Okay, let's start back at maps and let's focus on understanding this. Okay, maps. A map, also known as an associative array, is a collection of unique keys where each key is associated with a specific value. The relationship between a key and its value is called a mapping. Okay, mapping, key value pair, mapping. Maps support at least three operations: an add, where we have taken a key and a value, so we add a value associated with the key, create that mapping. Remove a mapping with the key, and then get the value based off of looking up for a mapping with a key. Okay, although, what's going on here? Okay. Merry Christmas, everyone. Forgot to say that. I might not be recording and just got notice about school related things. Okay, cool. Although a hash table is a type of map, not all maps are implemented via hashes. Instead of a hash table, maps can also use a self-balancing binary search tree to store their data. Although a hash offers better average case asymptotic complexity, see the section Algorithmic Complexity later in this chapter, a binary search tree has better worst case behavior, logarithmic versus linear, as we had said before, because a binary search tree, if it's balanced, is always going to be log n, versus like a hash table with like array, using array implementation with linked lists, it could kind of degenerate to just one big linked list. So a binary search tree also enables order preservation, so you can actually keep things in sorted order, enabling users to efficiently iterate over the entire collection in a sorted order. Finally, a binary search tree does not require a hash function. Instead, any key type is suitable so as long as it can define the less than or equal to operator. Okay, as long as we can tell whether or not something is less than or equal to, then it's fine. Although the general term for all collections mapping is mapping a key to a value, the name maps often refers specifically to an associated array implemented using a binary search tree as opposed to a hash table. For example, the C++ STL container std map is implemented using a self-balancing binary search tree, or any other similar data structure, because it provides the ability to in-order traverse the collection. The Linux kernel provides a simple and efficient map data structure, but it is not a general purpose map, so it's not general purpose. Instead, it is designed for one specific use case: mapping a unique identification number, UID, to a pointer. In addition to providing the three main map operations, Linux's implementation also piggybacks an allocate operation on top of an add operation. Linux's implementation also piggybacks an allocate operation on top of the add operations. Does that mean you need to allocate before you add, or is it that allocates happen inside the add? This allocate operation not only adds a UID value paired to the map, but also generates the UID. Oh, I guess adding will generate the UID for you. Okay, I guess the IDR data structure is used for mapping user space UIDs such as iNotify watch descriptors or POSIX timer IDs to their associated kernel data structure, such as the iNotify watch or KI timer structures, respectively. Following the Linux kernel scheme of obfuscated, confusing name, this map is called IDR. I said it last time, I was like, oh, that is so obvious. Anyway, initializing an IDR. Setting up an IDR is easy. First, you statically define or dynamically allocate an IDR structure, then you call IDR init. So you've statically define or dynamically allocate an IDR structure. So you create the IDR first, and then you pass in that IDR to IDR init. Okay? So for example, we statically define the IDR structure. So we don't do an allocation yet. We just define that to exist. And then we'll pass in the address. So to get the pointer to ID into IDR init. Okay, so we somehow initialize it. So then we're set up to be using it now. Allocating a new UID. Once you have an IDR set up, you can allocate a new UID, which is a two-step process. First, you tell the IDR that you want to allocate a new UID, allowing it to resize the backing tree as necessary. Then, with a second call, you actually request the new UID. This complication exists to allow you to perform the initial resizing, which may require a memory allocation without a lock. To discuss memory, we discussed memory allocations in chapter 12 and locking in chapters 9 and 10. For now, let's concentrate on using IDR without concern to how we handle locking. Okay, so assume like we don't need to think about concurrency and all that stuff right now. The first function to resize the backing tree is to IDR pre-get. Okay. So you can allocate new UID two-step. First, you tell the IDR that you want to allocate a new UID, allowing it to resize the backing tree as necessary. So we want to allocate a new UID. We request that, and then it resizes automatically. Okay. Then with the second call, you actually request a new UID. Okay. And it exists because we want to resize if necessary. Okay. All right. So the first function, the first part we had to do is to potentially resize by IDR pre-get. I don't know what this GFPT is, but this is going to be the IDR that we had initialized earlier with this call here where we passed ID hub. So, okay. So what is this GFPT? Let's see. This function will, if needed, to fulfill a new UID allocation, resize the IDR pointed at by IDP, which is any of your IDR structures. If a resize is needed, the memory allocation will use the GFP flags GFP mask. GFP flags are discussed in chapter 12. Okay, fine. Leave it be. You do not need to synchronize concurrent access to this call. Inverted from nearly every other function in the kernel, IDR pre-get returns 1 on success and 0 on error. Be careful. Oh my gosh. So IDR pre-get. Okay, so normally whenever we call these types of functions, right, like any other, I don't know, like Linux C or C type function, 0 usually means success. And anything non-zero usually is a bad thing. But with this function, IDR pre-get, we return 1 on success and 0 on error. Why? Okay. The second function to actually obtain a new UID and add it to the IDR is called IDR get new. So this will return a new UID. So it returns an int though. Interesting. So IDR get new struct IDP. It's a pointer to the IDR. And what is this? To obtain a new UID. Okay. What is void pointer? Is that like the value that the ID is going to be pointing to, and then we can just assign it to something, or what? Huh. And then IDs here. Okay, so let's see what it does. So this function uses the IDR pointed at by IDP to allocate a new UID and associate it with the pointer. Oh, so this is also adding too at the same time. So this function uses the IDR pointed at by IDP to allocate a new UID and associate it with the pointer PTR. On success, the function returns 0. Oh joy! And so this is the right. So this function adheres to the right expectations on return type or return value. On success, the function returns 0 and stores the new UID in ID. Okay, so ID will contain the UID. Pointer is the data we want to store when we do IDR get new. On error, it returns a non-zero error code, -E again, if you need to again call IDR pre-get, and E and node SPC if the IDR is full. Okay, so two different return values if on error. E again mean that we need to resize again, and SPC if the IDR is full, we can't add anymore. No space, I think. Error, no space. Error again. Okay. So let's look at a full example. Given this ID here, this is going to be our new UID. What we want is we want to check for pre-get. So if it is 0, return an error, because if it's 0 here, this will be true by nodding, like inverting it. And then that negation, this value becomes truthy, then no space. Okay, fine. Then we do get new, given our pointer, our IDR, and then we'll have an ID here. Get a return value, basically 0 if successful. And then if we'll just continue trying over and over again. If return value happens to be non-zero, but E again, error again. If it's error no space, then there's no point in trying this again, because that means the IDR is full. Okay. So if successful, the snippet obtains a new UID, which is stored in the integer ID and maps that UID to PTR pointer, which we don't define in the snippet. I think it's just for the sake of brevity, to be brief. The function IDR get new above. The function IDR, so this is a new function. The function IDR get new above enables the caller to specify a minimum UID value to return. Okay, so the declaration is this, starting ID. So this is a different one. Okay, this works the same as IDR get new, except that the new UID is guaranteed to be equal to or greater than starting ID. Okay, so it's just like the minimum. Using this variant of the function allows IDR users to ensure that UID is never reused, allowing the value to be unique not only among currently allocated IDs, but across the entirety of a system's uptime. This code snippet is the same as our previous example, except that we request strictly increasing UID values. Okay, int ID. So int pre-get, so try to resize if necessary. So same as before, return E no space. If we can't do that, can't resize. And then we do IDR get new above. Next ID is the minimum. And then we'll pretty much guarantee that this ID is going to be more than this. Okay. All right, is that what it is? Yeah. Specify minimum UID to return. I want to see if it's less than or greater than or equal to, or just greater. Yeah, greater than. Oh, guaranteed to be equal to or greater. Okay, so this will be the lower bound. So this will be the ID that is at minimum, and then everything else is valid. Okay. All right, and then if we don't have a good return value, or we do have a successful return value because it returns 0 if successful, IDR getting you above. So if it's 0, we invert that, we get non-zero, that becomes truthy. Then we increment the next ID for the next call. Okay, so this one will be the next minimum one. So looking up a UID. When we have allocated some number of UIDs in an IDR, we can look them up. The caller provides the UID and the IDR returns associated pointer. This is accomplished in a much simpler manner than allocating a new UID with the IDR find function. Okay, so this is to look up something with IDR and the UID. You get back a pointer to a void, which I think then you can just like cast to whatever you need to cast. So a successful call to this function returns a pointer associated with the UID ID in the IDR pointed by IDP. So this is actually pretty straightforward. It's probably one of the more straightforward functions. On error, the function returns null. Okay, that makes sense. I could buy that. Okay, no, if you mapped null to a UID with, okay, so it turns null because it's supposed to be a pointer to a void. So if it's a null pointer, that means there's nothing existing. So that makes sense to me. That's why. So note, if you map null to a UID with IDR get new or IDR get new above, this function successfully returns null, giving you no way to distinguish success from failure. So don't store nulls in IDRs. Consequently, you should not map UIDs to null. Exactly, because then you'll get confused. So usage is simple. Struct my pointer PTR. So this is the struct that you stored, the pointer to that specific struct called my struct type. You're just given this UID and the IDR, the pointer to the IDR. You can just do IDR find to get back the value, and then it'll return null if it's not successful. Straightforward, very straightforward. IDR find. Okay. So removing a UID. To remove a UID from an IDR, use IDR remove. So IDR remove. So we're just basically given the IDR and the ID, we remove, and there's no return. A successful call to IDR remove removes a UID ID from the IDR pointed at by IDP. Unfortunately, IDR remove has no way to signify an error. Okay. All right. Now it's time to clean up. So destroying an IDR. Destroying an IDR is a simple affair accomplished with the IDR destroy function, IDR destroy. So that's like freeing memory. A successful call to IDR destroy deallocates only unused memory associated with the IDR pointed at by IDP. It does not free any memory currently in use by allocated UIDs. Generally, kernel code wouldn't destroy its IDR facility until it was shutting down or unloading, and it wouldn't unload until it had no more users and thus no more UIDs. But to force the removal of all UIDs, you can call IDR remove all. Okay, let me read that again. A successful call to IDR destroy deallocates only unused memory associated with the IDR pointed at by IDP. So we have stuff in there that's not going to destroy. It's not going to like free up in this case. It's not free any memory currently in use by the allocated UIDs. Okay, so it's only unused space gets reclaimed. Generally, kernel code wouldn't destroy its IDR facility until it was shutting down or unloading, and it wouldn't unload until it had no more users, thus no more UIDs. But to force removal of all UIDs, like to do like a clean sweep, we can call IDR remove all, and that is the same sort of more or less signature as destroy, except that the name is different. It still takes in a pointer to an IDR called IDP. You would call IDR remove all on the IDR pointed at by IDP before calling IDR destroy, ensuring that all IDR memory was free. You would call IDR remove all on the IDR pointed at by the IDP before calling IDR destroy, ensuring that all IDR memory was freed. Okay, so it's saying that you should. Okay, so it's like two step if you want to really destroy the IDR. First, you have to get rid of all the UIDs allocated with this remove all. Once you've gotten rid of all the IDs, the UIDs, you need to just destroy the entire containing structure. So you call this first, and you call this one. Okay. Binary trees. Okay, so we're done with IDRs. That was actually not too bad. So a tree is a data structure that provides a hierarchical tree-like structure of data. Mathematically, it is an acyclic connected directed graph in which each vertex called a node has 0 or more outgoing edges and 0 or 1 incoming edges. A binary tree is a tree in which nodes have at most 2 outgoing edges. That is, a tree in which nodes have 0, 1, or 2 children. See figure 6.6 for sample binary tree. So this is a simple binary tree, just 2 children each node. Okay, not a search tree, just a regular tree. Notice how search trees will usually have the left node being less than the parent and the right node is supposed to be greater than the parent, but in this case we have 2 nodes, children here, that's actually greater than the parent. Okay, so binary search trees. All right. A binary search tree, often abbreviated BST, is a binary tree with a specific ordering imposed on its nodes. The ordering is often defined via the following induction. The left subtree of the root contains only nodes with values less than the root. The right subtree of the root contains only nodes with values greater than the root. All subtrees are also binary search trees. Okay, simple. We know that. A binary search tree is thus a binary tree in which all nodes are ordered, okay, such that left children are less than their parent in value and right children are greater than their parent. Consequently, both searching for a given node and in order traversal are efficient, logarithmic and linear respectively. So here is a sample binary search tree. Notice you have a parent, then you have a left child that is less than the parent, and then you have a right child that's greater than the parent, and that pattern holds for the rest of the tree here. So subtrees here, you take this subtree here, the 5 is less than the left child or the right child here with 6, and then it's greater than the left child with 4 here. Okay. So now here is where it gets interesting. Self-balancing binary search trees. Okay, so the depth of a node is measured by how many parent nodes it is from the root. So that's a depth, okay? How many parent nodes it is from the root. The depth of the node is measured by how many parent nodes it is from the root. So this depth here of 8, or this node 8 has a depth 1, 2, 3. Okay? So this one is at depth 1, so we have one parent. So it's counting by the number of parents from the root, I think. Yeah. So the height of a tree is the depth of the deepest node of the tree. So take the deepest node, and that's going to be the height. So it's going to be 3. Let's see. A balanced binary search tree is a binary search tree which is the depth of all these differ by at most 1. A self-balancing binary search tree is a binary search tree that attempts as part of its normal operations to remain semi-balanced. Meaning that whenever you add or delete a node, it's always going to do this rotation to actually get it to the point where you have like the deepest tree or the deepest node in the tree is always at most like 1 in terms of all the other nodes, all the learning nodes. So there's actually different types of self-balancing binary search trees. Red-black trees is going to be discussed right now, but there's also like AVL trees and splay trees and so on. But the red-black tree is the most important one, at least for the study of Linux, because that's what the Linux kernel uses, at least with 2.6 on various things. So red-black tree. A red-black tree is a type of self-balancing binary search tree. Linux's primary binary tree data structure is a red-black tree. Red-black trees have a special color attribute, which is either red or black. Red-black trees remain semi-balanced by enforcing the following 6 properties that the following 6 properties remain true. So it's always going to try to make these true, all of them. All nodes are either red or black. Leaf nodes are black. So leaf nodes of a red-black tree are always black. Leaf nodes do not contain data. So in a red-black tree, it kind of looks like this. This is like the. So this will be like null. That's black, right? And this will be null, and that's black. Okay, and then I believe that I think root is always what. So leaf nodes that contain data, so they're null. So we can just like normally represent it like this: null, null. Okay, and then all non-leaf nodes have 2 children. Okay, and if a node is red, both of its children are black. So this could potentially be red here. Okay. If the path from a node to one of its leaves contain the same number of black nodes as the shortest path of any other leaves. So it looks kind of like basically if we were to say, and I think root is always black too. So let's say we had something like this, okay? Oops. So we had something like this, and then we'll also have more nodes. And let's just say they're black here, and then these are null. this actually would not be a red-black tree because I think the path, any one of these paths, right, has to have the same number of black nodes in this case. Okay, so that's not a red-black tree. One of them would have to be colored red in this case. So yeah, you're just basically rebalancing this tree by rotating. Like let's say you have this right here, you'll just rotate that node until you actually get all 6 rules back to being true, and then you have a self-balanced tree. Not sure if it's worth like going too deep into it, but let's just keep reading, and then maybe if it's worth it, we can see more examples. So. Okay, so taken together, these properties ensure that the deepest leaf has a depth of no more than double that of the shallowest leaf. Okay. Consequently, oh yeah, but I didn't even read all this, huh? Okay, all non-leaf nodes have 2 children. Okay, so you have to have a parent. If you're a parent, you have to have at least 2 children. If a node is red, both of its children are black. The path from a node to one of its leaves contains the same number of black nodes as the shortest path to any of its other leaves. Okay, that means all paths have to have equal black nodes. Taken together, these properties ensure that the deepest leaf has a depth of no more than double that of the shallowest leaf. Consequently, the tree is always semi-balanced. Why this is true is surprisingly simple. First, by property 5, if a node is red, both of its children are black. A red node cannot be the child or parent of another red node. So consecutive red nodes are not allowed in a red-black tree. By property 6, all paths through the tree to its leaves have the same number of black nodes. The longest path through the tree alternates red and black nodes. Thus, the shortest path, which must have the same number of black nodes, contains only black nodes. Therefore, the longest path from the root to a leaf is no more than double the shortest path from the root to any other leaf. If the insertion and removal operations enforce these 6 properties, the tree remains semi-balanced. Now, it might seem odd to require insert and remove to maintain these particular properties. Why not implement operations such as they enforce other simpler rules that result in a balanced tree? It turns out that these properties are relatively easy to enforce, although complex to implement. And that's the reason why I actually tried implementing this on my own, and it was just like horrible in terms of like, it just took too long because it was just complex to implement. But the behavior is actually quite elegant. So anyway, the effect basically. Allowing insert and remove to guarantee a semi-balanced tree. So basically every time you insert or remove a node to and from a tree, you have to actually do some rotation and recoloring operations in order to keep the tree semi-balanced without the burdensome overhead. Okay. Describing how insert and remove enforce these rules is beyond the scope of this book. Okay. Although simple rules, the implementation is complex. Again, the implementation is complex. Any good undergraduate level data structures textbook ought to give a full treatment. Maybe one day we'll visit it. rbtrees. The Linux implementation of red-black trees is called rbtrees. So that's what it's called. Okay, they are defined in lib.rbitree.c and declared in rbtree.h. So remember we were like working with the scheduler, and we had access to an some of these rbtree functions. So this is where it comes from. The scheduler is the queues are based off of these red-black trees, as I think was mentioned earlier in the book. So yeah. Aside from these optimizations, Linux's rbtrees resemble the classic red-black tree as described in the previous section. They remain balanced such that inserts are always logarithmic with respect to the number of nodes in the tree. So we'll probably just check that out real quick. rbtree.h. Okay. So, whoa, that's a lot. By Andrea Arcangeli, Susa. So this is from a SUSE Linux person. Okay, so Whew, this is complicated, but we can see that it does some recoloring here and all that stuff. Anyway, that's like comments. So let's look at some, maybe the header might have some implementation. Let's see. Ooh, it's quite short. Let's see. rbtree.c. Okay. Ah, yeah, rotation code looks exactly like what you would do in computer science course. Rotate, it's probably, yeah, rotate left. Okay, so that you're just swapping pointers around, redoing parents and grandparents and stuff like that. Then you have a rotate right here. Okay, and then you'll have insert color, whether or not it's red or black, and you have like uncles and okay, yeah, this is all coming back to me. You need to consider like uncles, grandparents, cousins, stuff like that in order to fully work with the red black tree. So this is the complexity we're talking about here. Actually, erase color means to make it a red black. So yeah, so there's a lot of stuff here. And then erase is probably just a delete. Okay, and then let's see something where first, so returns the first node in sorted order. The trees to the leftmost. See how it just while the node. So you're the root node right here. Take the node. Basically, it's probably just containing that node. So it's probably similar to like the whole linked list where you have a list head. This is our B node, which just contains probably left and right. So we just basically iterate left until we can't go left anymore, and then we just return that node. And then last would be right, go all the way right. And then next would be the next, I guess, in order successor. So yeah, see how this loops. Basically, you start at the right child, right? Because that's going to be your in order successor. But if you have a tree to your left, a child to your left, you want to actually just keep going left all the way in the bottom until that is going to have no more children, and that's actually your in order successor right there. So yeah, previous would be the in order predecessor. Let's see. Yeah, that's about it. I mean, it's not too bad. It's just it's if you know how to do rbtree, like it feels like a standard rbtree just in terms of kernel code. Not gonna stress about it actually. Okay, so let's continue. Okay, so the root of an RB tree is represented by the RB root structure. To create a new tree, we allocate a new RB root and then initialize it with the special value RB root. Okay, so we just basically declare one and just initialize it with RB root. Okay, it's a value. Okay, so individual nodes in an RB tree are represented by the RB node structure. Given an RB node, we can move its left or right child by following pointers off the node of the same name. The RB tree implementation does not provide search and insert routines. So we can't find things in that way. Huh. Okay, users of RB trees are expected to define their own. This is because C does not make generic programming easy. Yeah, that's true. And the Linux kernel developers believe the most efficient way to implement search and insert was to require each user to do so manually, providing RB tree helper functions, but their own comparison operators. Yeah, that's the reason why, because searching type of operations is like so tied to your use case, you might as well just do it yourself. The best way to demonstrate search and insert. Oh yeah, and the insert part is, yeah, you have to write down your own. That's the reason why it's really horrible, because you had to also like do the rotate. You had to know when to rotate and recolor and things, but the helpers are there. Okay, so first, so this is going to be an implementation of a search. So The best way to demonstrate search and insert is to show a real-world example. First, let's look at search. The following function implements a search of Linux's page cache for a chunk of a file, represented by an inode and offset pair. Each inode has its own RB tree keyed off of page offsets into a file. This function thus searches the given inode's RB tree for a matching offset value. Okay, so here's an example of a search. So what we want to do is we want to first get the RB node. Okay, given the inode here, we have the page cache. Each page cache has RB node associated with it. And then if it's not null, while it's not null, we basically search for the page, finding, okay, so RB entry is going to be like the container of for list head. We just get the entry given the RB node here, the type, and then the member name. Yeah, I remember this. Okay, so that will get us back the containing thing, right? So I'm guessing here that struct page has a RB page cache inside, its struct definition that is actually going to be an RB node type, and this is the pointer we're interested in. Okay, and then it's simple, right? Like if the offset is less than what the page offset is, we go left, because that's, we go left child, it's less than. If it's greater than, we will go right. Else we'll just, it's equal, so that's what we have it. So we just return that. We found the page. So it's just like your regular binary search tree. Searching is easy, insert not so much. Right here. And I bet you it's long. Oh, not too long. Okay, so in this example, the while loop iterates over the RB tree, traversing as needed to the left or right child in the direction of the given offset. So yeah, so it's RB tree is just the same thing as a binary search tree, except that it just self-balances, and there's just like a bunch of other rules that have to hold in order for it to like be considered a balanced binary search tree. The if and else statements implement the RB tree's comparison function, thus enforcing the tree's ordering. If the loop finds a node with a matching offset, the search is complete. So this is like your straightforward regular binary search tree search. Okay. Okay. And the function returns associated page structure. If the loop reaches the end of the RB tree without finding a match, one does not exist in the tree, and thus the function returns null. Insert is even more complicated because it implements both search and insertion logic. The following isn't a trivial function. Yep, I knew it. Insert's going to be hard. But if you need to implement your own insert routine, this is a good guide. So we got to just follow something like this. So given double pointer, so we want to get the address of the address, so the address of the pointer of the RB node given the inode. Okay, so first take the inode, get the pointer to the RB node, and then get that address of that RB node. Okay, then we initialize a parent to null, and then we want to basically get the this is going to be the page that we're inserting, I guess. Yeah. No, the page that's going to be the new parent, I think. Sure. Okay. So first we initialize the parent to be the current node, which is P here. Okay, the pointer. And then we're going to get the entry of that page that was associated with our RB node. Again, like the list head container of. And then we do our searching for the most appropriate place. Then we link. Okay, we link. Let's see. So P is going to be the one that's going to be linking with node. Node would be the node we want to link with. Parent. So this is a node. Node is going to be a thing that we want to add to the tree. And then P is going to be the parent of this node, I think. Yeah, I guess. But what's parent? Is that? Oh, that is the pointer to the parent. Okay, the parent. So parent and node are going to be linked. I don't know what the P is because it looks like it's already, it's right here. It's already assigned. Probably just a member name or something like that. Interesting. Oh, no. This is different. This is the double pointer. This is a single pointer. I see. Okay. They're same thing is that this is the address of parent. Okay. This is the address of the pointer of parent. Then after that, we just color a node, which I think will cause the rotation and recoloring based off of node here. Okay. Not going to go into that too deeply. So anyway, as with our search function, the while loop is iterating over the tree, moving in the direction of the provided offset. Unlike with search, however, the function is hoping not to find a matching offset, but instead reach the leaf node that is the correct insertion point for the new offset. So yeah, we're trying to find the parent of this new node that we're inserting. When the insertion point is found, rbLink node is called to insert the new node at the given spot. rbInsertColor is then called to perform the complicated rebalancing dance. So basically the rotation and the recoloring. The function returns null if the page was added to the page cache, and the address of the existing page structure if the page is already in the cache. Whew. Okay. All right, so what data structure to use and when? All right. So thus far, we've discussed 4 of Linux's most important data structures. Linked list, which I really wanted to spend time understanding because I think that's like the basics of queues, maps, and red-black trees. In this section, we cover some tips to help you decide which data structure to use in your own code. So let's see, which one do we use and when? If your primary access method is iterating all over your data, use a linked list. Intuitively, no data structure can provide better than linear complexity when visiting every element. So you should favor the simplest data structure for that simple job. So if you're going to visit every single element in some data structure, linked list is your go-to. Also, consider linked lists when performance is not important, when you need to store a relatively small number of items, or when you need to interface with other kernel code that uses linked lists. If your code follows the producer-consumer pattern, use a queue, particularly if you want or can cope with a fixed size buffer. Queues make adding and removing items simple and efficient. They provide a first in, first out FIFO semantics, which is what most producer and consumer use cases demand. On the other hand, if you need to store an unknown, potentially large number of items, a linked list may make more sense because you can dynamically add any number of items to the list. And then you can just kind of emulate a queue by just taking like the head or whatever that way. Let's see. If you need to map a UID to an object, use a map or that IDR data structure. Maps make such mappings easy and efficient, and they also maintain and allocate the UID for you. Linux's map interface being specific to UID to pointer mappings isn't good for much else. However, if you are dealing with descriptors handed out to user space, consider this option. Now, if you need to store a large amount of data and look it up efficiently, consider a red-black tree. Red-black trees enable the searching in logarithmic time while still providing an efficient linear time in order traversal. Although more complicated to implement than other data structures, their in-memory footprint isn't significantly worse. If you are not performing many time-critical lookup operations, a red-black tree probably isn't your best bet. In that case, favor linked lists. So none of these data structures fit your needs? The kernel implements other seldom used data structures that might meet your needs, such as radix trees. So basically, the Linux kernel does provide other data structures too. So radix trees, which is type of trie, and bitmaps. Okay. Only after exhausting all kernel provided solutions should you consider rolling your own data structure. So remember, it's discouraged to roll your own. One common data structure often implemented in individual source files is the hash table, because the hash table is little more than some buckets and a hash function. And the hash function is so specific to each use case, there's little value in providing a kernel-wide solution in a non-generic programming language such as C. And that's where we hit the limitation of C, the lack of generic programming. Algorithmic complexity. Often in computer science and related disciplines, it is useful to express the algorithmic complexity or scalability of algorithms quantitatively. Various methods exist for representing scalability. One common technique is to study the asymptotic behavior of the algorithm. This is the behavior of the algorithm because its inputs grow exceedingly large and approaches infinity. Asymptotic behavior shows how well an algorithm scales as its input grows larger and larger. Studying an algorithm's scalability, how it performs as the size of its input increases, enables us to model the algorithm against a benchmark and better understand its behavior. What's an algorithm? All right, well, an algorithm is a series of instructions, possibly one or more inputs, and ultimately a result or output. For example, the steps carried out to count the number of people in a room are an algorithm, with the people being the input and the count being the output. In the Linux kernel, both page eviction and process scheduler are examples of algorithms. Mathematically, an algorithm is like a function, or at least you can model it as one. For example, if you call the people counting algorithm f and the number of people to count x, you can write y equals f of x. Given x number of people, count the number of people using the function f, where y is the time required to count the people x, or x people. Big O notation. One useful asymptotic notation is the upper bound, which is a function whose value after an initial point is always greater than the value of the function that you are studying. It is said that the upper bound grows as fast or faster than the function in question. A special notation, big O, pronounced big O notation, is used to describe this growth. It is written f of x as O of g of x and is read as f as big O of g. Oh, okay. The formal mathematical definition is if f of x is O of g, then there exists a c x prime such that f of x is less than c c times g of x for all x greater than x prime. Okay, whatever. In English, the time to complete f of x is always less than or equal to the time to complete g of x multiplied by some arbitrary constant. Oh, this is multiply. Okay. So, okay. Yeah, I got it. So as long as the input x is larger than some initial value x prime. Essentially, you are looking for a function whose behavior is as bad or worse than the algorithm. You can then look at the result of large inputs to this function and obtain an understanding of the bound of your algorithm. Okay. Big theta notation. Okay. All right, cool. When most people talk about big O notation, they are more accurately referring to what Donald Knuth describes as big theta notation. Technically, big O notation refers to an upper bound, so we commonly mistaken big theta as big O. So. Okay. So for example, 7 is an upper bound of 6, so are 9, 12, and 65. Subsequently, when most people discuss function growth, they talk about the least upper bound, or a function that models both the upper and lower bounds. Professor Knuth, the father of the field of algorithmic analysis, describes this as big theta notation and gives the following definition. Okay, so let's see what the definition is. Okay. If f of x is big theta of g of x, then g of x is both an upper bound and a lower bound for f of x. If f of x is big theta of g of x, okay, if it's theta of g of x, like, theta of n, that means f of x is linear, then g of x is both an upper bound and a lower bound. Okay, so on average. Okay, so then you can say that f of x is of order g of x, The order or big theta of an algorithm is one of the most important mathematical tools for understanding algorithms in the kernel. Consequently, when people refer to big O notation, they are more often talking about the least such big O, the big theta. You really do not have to worry about this unless you want to make Professor Knuth really, really happy. I do. The art of computer programming. Time complexity. Consider the original example of having to count the number of people in the room. Pretend you can count one person per second. Then, if there are 7 people in the room, it will take 7 seconds to count them. More generally, given n people, it will take n seconds to count everyone. Thus, you can say this algorithm is O of n. What if the task was to dance in front of everyone in the room? Because it would take the same amount of time to dance whether there were 5 or 5,000 people in the room, this task is O of 1, or constant time. See table 6.1 for other common complexities. Okay, so constant is 1, log n, logarithmic, and linear, and squared, quadratic, and cubic. 2 of n is exponential, and n factorial is factorial. So this is like the worst. This is like never going to finish, basically. This is the fastest. Okay, we always want to get our algorithms between maybe these 3 here. If we're going to do something complex. Probably not n squared. N squared is probably too slow. Maybe. I don't know. Okay. What is the complexity of introducing everyone in the room to everyone else? What is the possible function that models this algorithm? If it took 30 seconds to introduce each person, how long would it take to introduce 10 people to each other? What about 100 people to each other? Understanding how an algorithm performs as it has ever more work to do is a crucial component in determining the best algorithm for a given job. Of course, it is wise to avoid complexities such as O of n factorial, or O of n 2 to the n, or O of 2 to the n, because that's exponential versus n factorial. Those are really slow. Likewise, it is usually an improvement to replace an O of n algorithm with a functionally equivalent O of log n algorithm. This is not always the case, however, and a blind assumption should not be based solely on big O notation. Recall that given O of g of x, there is a constant c multiplied by g of x, because we usually drop the constant. Therefore, it is possible that an O of 1 algorithm takes 3 hours to complete. Sure, it's always 3 hours regardless of how large the input, but that can still be a long time compared to an O of n algorithm with few inputs. Yes, the typical input size should always be taken into account when comparing algorithms. So you have to, like, when you're thinking about your algorithms and time complexity, you always have to think about, like, what is your expected number of inputs. Like, you can't really just say, oh, like, if it's scaled to like 1 billion elements, when probably it's never going to be 1 billion elements, then there's no point in thinking about it that way. So favor less complex algorithms, but keep in mind the overhead of an algorithm in relation to the typical input size. Do not blindly optimize to a level of scalability you will never need to support. Yeah, that's like the common mistake. Everyone likes to think they're Google. We're dealing with Google amounts of data. Okay. So, and that's the reason why you make things harder than what they should be to maintain, to implement, because you want to be handling Google-sized data sets, which is not the case for a lot of people. Okay, conclusion. In this chapter, we discussed many of the generic data structures that the Linux kernel developers use to implement everything from the process scheduler to the device drivers. You will find these data structures useful as we continue our study of the Linux kernel. When writing your own kernel code, always reuse existing kernel infrastructure and don't reinvent the wheel. We also covered algorithmic complexity and tools for measuring and expressing it, the most notable being big O notation. Throughout this book and the Linux kernel, big O notation is an important notion of how well algorithms and kernel components scale in light of many users, processes, processors, network connections, and other ever-expanding inputs. Done. All right. Whew. Good. We finished another chapter. Data structures. I wouldn't worry too much about it right now if it sounds too crazy. I think for sure throughout the book they're going to introduce the same data structures again, and then we'll get more practice. So, thank you.